We already covered a lot of the preliminary vocabulary for this section in 5.3, so we can jump right into it this time. The median of a triangle is a line segment whose endpoints are one vertex of the triangle and the midpoint of the side opposite from the vertex. It makes more sense if you see one drawn in. That's a median. A triangle has three medians, one for each vertex, and those three medians are concurrent. So let's draw them in and see where they all intersect. The point of concurrency of the medians of a triangle is known as the centroid. Hello, Mr. Centroid. This will make many of you happy, but the centroid will always be on the inside of the triangle. There are a couple of special properties for a centroid. The first is that the centroid is 2/3 the distance from each vertex to the midpoint of the opposite side. This is one of those cases where very few people get the concept based on the theorem. It isn't immediately obvious what it means from the wording, so I will present what it means to you in a few different ways, and hopefully one of them will click for you, and you will understand how to use them in the problems you are given. The centroid splits up each median into 2/3 and 1/3 pieces. The 2/3 side should be obvious based on the picture. Officially, it is always the side with the vertex. That gives us these formulas. AM is 2/3 the length of the whole median AX, BM is 2/3 the length of the whole median BY, and CM is 2/3 the length of the whole median CZ. That's what the definition says. Well, let's look at it some other ways. I mentioned that the centroid splits up each median into 2/3 and 1/3 size chunks. This is what that looks like. Each one is split into 2/3 and 1/3, or this is a popular way to go about it. You should know that 2/3 is twice as big as 1/3, so the 2/3 side of the median is twice as big as the 1/3 side. In this case, AM is twice as big as MX. That is very handy when solving problems using the centroid. As an example, if you know that MY equals 8, then you know that MB is going to be twice that, or 16. Hopefully one of these methods makes sense to you. Somehow you need to be able to work with the fact that the centroid sits 2/3 of the way from the vertex. There are a couple of other properties of the centroid, but they aren't really necessary for this course. They are just interesting side notes. Well, at least I think they're interesting. Drawing in all three medians ends up making 6 small triangles. These 6 small triangles all have the same area. They usually aren't congruent, but they do always have the same area. That's kind of cool. The other special but not truly necessary fact about the centroid is somewhat related to the last fact. The centroid is also known as the geometric center or the barycenter. These are more complicated terms than we need, especially for an interesting fact that isn't even necessary for this course. But they both lead to the conclusion that the centroid is the center of mass for a triangle. So if you cut out a triangle with some rigid material, like cardboard, made sure your measurements are perfect, cut straight, and the cardboard is equally dense and thick at all spots, then the triangle would balance on the head of a pen or a pencil at that center of mass spot. I think that's kind of cool too. Now let's get back to things which you are required to know. We are now dealing with the altitude of a triangle. What does the word altitude mean to you? What do you think about? For many people, they think about how far something is off the ground. Sometimes that should probably be sea level instead of the ground, but most people like to think of it as the ground, which works for our discussion for now. So here I have a bird flying merrily along. The altitude of that bird is how far away it is from the ground. From a couple sections ago, we know that the distance from something, the bird, to a line, the ground, is the shortest distance. And the shortest distance is the perpendicular, like this. But that's the basic idea for altitude. How far off the ground is it? The altitudes of a triangle work the same way as that bird. Here I have a triangle with vertex A. If I want to draw in the altitude from A, I am asking how far off the ground that is. The ground would be the opposite side. I want to draw in the shortest distance, which would be the perpendicular, so that would be this line segment here. That red dotted line is the altitude from A. If we were building a strange triangular building, that is how far A would be off the ground. Students are usually pretty okay with that idea for A, and this triangle here. But then things get a little weird when I have a picture like this. What happens if I want to find the altitude from B? Isn't that already on the ground? When dealing with this, you have to realize that the ground is always the side opposite your vertex. So for B, this is your ground. Remember, that is your opposite side. Many students find it helpful to turn the page until the ground is level with them. So by turning the page, the triangle will shift around and eventually the ground will be horizontal and level with you. From this vantage point, many students have an easier time comprehending the altitude from B. If this is helpful to you, by all means, turn your page around to get a better viewpoint. Oriented like this, it should be pretty easy to draw in the altitude. So that's what happens with an acute triangle. It starts to get a little weird with right and obtuse triangles. What happens with the altitudes in a right triangle? The one from point C is pretty normal. What about the altitudes from A and B? The altitudes are already there. The legs of the right triangle are already altitudes. They're already drawn in. All three of the altitudes actually meet at vertex C. An obtuse triangle has one normal altitude and two little bit weird ones. First, the easy one. From the obtuse vertex angle, you simply draw the perpendicular to the opposite side. No problem. The obtuse angle plays very nicely. Here's the same triangle, but I rotated it so that one of the other angles was in the air, and its opposite side, the ground, was horizontal. What happens now? How far is vertex A off the ground? Think about it like a building. What if you climbed up to A and then dropped a rock? Where does it fall? It certainly doesn't fall into the triangle. It would fall outside of the triangle. So this is why it is a little weird. In order to accommodate our altitude, we actually need to extend out our ground. With the ground extended out, we can successfully draw in the altitude from A. The same weirdness happens from the other acute vertex angle, point C. You need to extend the ground out for that one too. Here's what that would look like with all three altitudes drawn in for that obtuse triangle. Notice how there are two sides, the brown ones, which have been extended out in order to accommodate the altitudes from the acute angles. The altitudes of a triangle are concurrent. The point of concurrency of the altitudes of a triangle is known as the orthocenter. The circumcenter, incenter, and centroid all have special properties we have gone over, and that you need to know. The orthocenter has none. Makes it easy. Man, he's a whiner. So now let's look at where these orthocenters end up in various triangles. With an acute triangle, the orthocenter ends up on the inside of the triangle. With a right triangle, the orthocenter ends up being the vertex of the 90-degree angle. Therefore, in right triangles, the orthocenter is on the edge of the triangle. With an obtuse triangle, the orthocenter ends up being on the outside of the triangle. Some of you won't be happy with that, I know, but there it is. Here's a quick summary from the last two sections. The incenter and centroid will always be on the inside of the triangle. Easy. The circumcenter and orthocenter will be on the inside of an acute triangle, on the edge of a right triangle, and on the outside of an obtuse triangle.